Good morning. I'm delighted to be here. My name's Kemal Malik. I'm a member of the Board of Management of Bayer. And what I want to do is talk to you a little about what I think are going to be game-changing technologies that are going to influence medicine for many years to come. Now, I work for a company that's 153 years old. And as I wandered around this morning, I realized that makes it an awful lot older than many of the companies here. And me personally, I think I'm at least twice as old as most of the people here. But I want to talk a little bit about how even a company our age can be part of what I think is a revolution in the life sciences. And why do I say there's a revolution in the life sciences? When I was a junior doctor, to look at a protein, work out its chemical structure, what it did in the body, was the basis of people's PhDs. They spent 3 years doing it. We can now do it in 7 seconds. Gene therapy was this really big excitement in the 1990s. We were going to cure genetic diseases with gene therapy. And in 2002, that came to an abrupt end because there was a tragic death of a young man due to an immune reaction. And yet last year, we had the first gene therapy approved for use. And the big thing that's happened in the last 15 years is the understanding and sequencing of the human genome. The genome is our genetic information. This project took 15 years and cost nearly $3 billion to do. You can now sequence the human genome for less than $1,000, and it takes 2 hours. There is a revolution going on in the life sciences, and it's happening for 2 reasons. The first is, as I've said, our understanding of genetic information, the genome. But the second reason is around technology. We've got amazing computational power now. We've got the ability to collect and analyze enormous amounts of data. And we have the ability to share that so people can work on the same data sets around the world. And so those 2 things in combination are revolutionizing medicine. When I was a junior doctor in the 1990s, I enjoyed my life. But I remember speaking to a professor at the time who I was working for and saying, I spend a lot of time treating people, but I never cure people. And apart from people who had acute infections, you never really cured people. People with blood pressure and stroke and heart attacks, you never cured them, you just treated them. And I said, when are we going to start curing people? And he said, well, maybe one day in the future. Let me talk about why I think that might be happening. And I want to talk about 2 technologies that I think are going to influence all of us. The first one is DNA editing, and the second one is cell therapy. And I'm going to talk about both of those in turn. Let me start with DNA editing. And I'll give you a little bit of a background about DNA. And that picture shows DNA. I talked about the human genome. That's your genetic information. And the basic building block component is your genes. Your genes are what make you who you are. They make you different from the other 7 billion people on Earth. But also they make you different from the 107 billion people who have ever lived on Earth. And that is pretty unique. Yes, people will say to you, you've got your grandfather's eyes, you've got your mother's smile, and that's obvious because you inherit your genetic information, but it is unique to you. And we think that there's probably about 25 to 30,000 genes in total in the human body. And those genes code for proteins. If you want to think about it, genes are codes. They code for proteins. And proteins are the things that build your body up, they make your intracellular processes work, they make your body function. So genes make proteins. And the code is written in DNA. DNA is the language that our genes use to make proteins. And if you stretch out the DNA in a cell, it's probably about 2 meters long, but it's all twisted up and it occupies a space about 6 microns. So it's incredibly complex, but that's what we are as human beings. Now, most of the time, it works really well and we're healthy. But occasionally, those genes don't make proteins. They're faulty. And a lot of the time, that doesn't actually matter. But sometimes it does. And there's inherited conditions, hemophilia, sickle cell anemia, cystic fibrosis, which are dreadful diseases because there's a mutation, there's an error in the genes that make proteins. Cancer is a disease of your genome. It's sometimes caused by external insults. If you smoke, if there's exposure to the sun, that damages your DNA. And as a result, bad things happen. So the holy grail, obviously, is can we find the bad bits of DNA in these diseases and correct them? And that was the basis behind gene therapy. Now, it's a bit of a challenge because what you're doing is injecting the gene with a virus, hoping it finds the right place in the body, does the right thing, and works. So gene therapy has had, I guess, to be fair, a fairly checkered history. And I talked about the tragic case in 2002 where a young man, Jesse Eisinger, died as a part of being in a clinical trial in gene therapy. What's really caused a huge amount of excitement is a new technology called DNA editing. If you go into Google and type in DNA editing, you'll get thousands of hits, but those hits will be from the Wall Street Journal, the New York Times, The Economist. They won't necessarily be from scientific magazines, because this is a technology that has the ability to fundamentally change mankind, and I'm not exaggerating. What is it? It's, in essence, molecular scissors. These are scissors that go in, find the bad bit of DNA, snip it out, and replace with good bits. It's in essence like a word processor with find and replace. Now, when you heard me say that this DNA is 2 meters long and 6 microns wide, you can imagine how sophisticated this is. The technology is called CRISPRCas. And a way I heard it described was really well was, imagine Hamlet's Shakespeare. And you had 5,000 copies of Hamlet's Shakespeare. And in one of those copies, instead of having to be or not to be, you had to be or to be at Slush. And you needed to find the faulty one in one of those 5,000 volumes, in that one line, snip it out and put in instead to be or not to be. That's what this technology is about, and that's how sophisticated it is. The applications are wide. Inherited diseases, where there's a faulty gene, you go in, cystic fibrosis, hemophilia, all of these awful diseases that affect kids around the world. But also cancer, where you can go in, snip out the gene, and put a healthy gene in. But outside healthcare, in agriculture, it has the opportunity to yield better crops. You can modify crops. Fantastic, isn't it? Well, this is a magazine I guess some of you read called Wired. And it says in here, no hunger, no pollution, no disease, and the end of life as we know it. And people are worried about this technology. And I guess they're worried for 2 reasons. There's a practical one and a philosophical one. The practical one is, does it have effects away from where you want it to have the effects, off-target effects? The other concern is philosophical. Are you playing God by doing this? Well, to be fair, every time a doctor does an intervention, you could say that's not in the natural order of things. If you're a caveman and you got ill, you died. Nowadays, we intervene. So I don't think that's as important. What is a concern is you can use this technology in embryos. You could use this to alter every cell in the human body, including egg and sperm, which means that you can genetically manipulate generations. We can make people smarter, taller, brighter, all of those things. Do we really want to do that as a society? Probably not. And so there's a moratorium on this use in germ cell lines, in embryos. It can be done. Scientists in China have done it, but there is a moratorium around the world around this technology. Why is Bayer interested? We've signed a joint venture with a company called CRISPR Therapeutics to develop this in certain diseases. We're investing up to 400 million over the next 5 years to develop this in heart disease and some other indications. This technology has a capability of revolutionizing medicine. And I'm not normally prone to exaggeration or hyperbole, but genuinely. I want to quickly turn to a second technology, which is cell therapy. Bayer is often credited with being the founder of the modern pharmaceutical industry. In 1898, a bioscientist, Felix Hoffmann, synthesized aspirin, and that's seen as the birth of the modern pharmaceutical industry. The next 80 years, most of the treatments we had were chemicals, chemistry made in laboratories. And then the second big wave of innovation was the use of proteins, large molecules, by companies like Genentech and Amgen. We're on the cusp of a third wave of innovation, which is the use of living cells to treat illnesses. And there's a variety of these going to be used, but I'm going to talk about stem cells. Stem cells are the basic building block of your body. Every cell in your body started as a stem cell. So you're made up of cells that have been ultimately derived from stem cells. Now, there are 3 types of stem cells. There's embryonic stem cells. And that's the one where there's been huge controversy, particularly in the United States, where, yes, they could do work. No, then the Republicans came in and said, no, there couldn't be any work. And it's, I guess, a religious, socioeconomic, philosophical debate about the embryonic stem cell use. There are certain adult stem cells in the heart, the kidney, and the brain, but they can only make heart, kidney, and brain cells. And the great thing about embryonic stem cells is they can make every single cell in your body. The really cool thing is there's now a third type of stem cell called induced pluripotential stem cells, iPSCs. And for the work that developed these stem cells, 2 people, Yamanaka and Hübner, won the Nobel Prize in Medicine in 2012. And what they did was something very cool. They said, can you take cells, mature cells like skin or hair or teeth, and turn those cells by using programming agents into stem cells? Stem cells have the capacity to become any cell in the body. Can you take a hair cell, turn it back to being a stem cell, and then use it to turn into any cell in the body? That was their theory. They did some initial work in animals and showed, yes, we can get these stem cells and we can make them into, we can get these ordinary cells from mice and from humans, and we can turn them into a stem cell-like state. The next thing was, can we turn them into cells of an organ? And they showed they could do that. And now, stem cells are in clinical trials. In Japan, they're being used to treat blindness. So, you can take cells from any of us, just scrapings of your skin. You can turn them into stem cells, and then you can allow them to differentiate and become new cells. So, imagine, someone has a heart attack and damages their heart. You take their skin cells, you reprogram them, you inject the cells back into their hearts, and they become functioning heart cells again. That is extraordinary. Can you imagine things like Parkinson's, strokes, all of those neurodegenerative disorders where you can change what people are doing? Once again, there will be big ethical issues around this. Is it safe to do this? These are living cells that you're injecting into human bodies. And so there will be a lot of checks and balances that we need to apply. But the combination of gene editing and DNA technology allied with stem cells is going to change the world. So if I had that professor of medicine here today, I'd say to him, you know what? You told me it'd be the future. Well, actually, the future's here now. I genuinely believe we're at the cusp of curing disease. We need to handle the ethical issues. It's not for multinationals to make those decisions. It's not for scientists to make those decisions. We need governments, that's why we elect them, to make those decisions. We need society to engage in this, and that's why I wanted to come here, because society needs to engage in these sort of discussions. Are we comfortable with altering people's DNA? Are we comfortable about injecting stem cells? You need to make those decisions, not multinationals, not scientists. And the other reason why I wanted to be here is no company can do this alone. This is about connectivity. It's about working with companies like your own, small companies, large companies. The work we're doing with DNA editing that I talked about is partnering with a very small startup company, which is venture capital funded, which is taking us to the next level. We're going to be announcing something with stem cells, once again, partnering with small companies and scientists. We're all part of an ecosystem, hopefully to make the world a better place. Thank you very much for your time.